How do we determine pKa's? Right, I told you, as you know, pKa is a fundamental property of the chemical nature of the acid or the base. But how do we determine it, right? I mean, you can look it up in tables. I know, it's the modern world. You can look everything up on the internet and find it. But where do those numbers come from? And the way that they're determined experimentally is by a procedure known as titration that you probably all did in high school chemistry. And what titration involves is the addition. It's an analytic method that's used to determine the amount of acid in solution. Let me give you an exact definition. Titration. It's an analytic method used to determine the amount of acid in a solution. And the idea is that we add in, we have a solution, we want to figure out how much acid is in it, and so we keep titrating in larger and larger and larger amounts of a base. Okay, and so let's figure out experimentally where that pKa for acetic acid came from. And what we're going to do, as I said, is we're going to titrate in some base, and we're going to keep measuring what happens to the pH as we do that. And we're going to make a plot of the pH as a function of the amount of base that we add. Okay, so we're going to plot the pH versus the amount of base. And in this case, we're going to use hydroxide anion that we add. And let's consider, for example, 100 mils of 1 molar acetic acid. Okay. So we have a total here of 0.1 moles. Okay. And we're going to see what happens. Now we have two reactions that we have to keep track of here. Okay. The first reaction is the one you know about. We have this acid that we're going to dissociate into its conjugate base, the acetate anion, plus a proton. Okay? That's our first reaction. And the second reaction, of course, is just the ion product of water. Hydroxide anion plus a proton really goes in this direction to give us H2O. And what's happening here? Well, what's happening here, of course, as you recognize, is that as I begin to add in increasing amounts of base, as I start to add more and more of this, I'm going to drive the reaction this way. And in the process, because these two reactions are occurring in solution, I'm going to force more of the acid to dissociate into the conjugate base, and so that I can consume these protons with the hydroxide. That part makes sense? That's just Le Chatelier's principle, right? The more base I add, the more I dissociate the acetic acid into the acetate anion. Okay? And so what I want to plot now on two boards, you do it on these boards, is I'm going to plot here relative abundance of something. %, 100%, 0%. This is the abundance. Okay? And on this axis, 0, 1, 0.5. This is what we're going to call, on this axis, the equivalence of base. And by equivalence, I mean the amount of base that's equivalent to the total amount of acid I have in the solution. Okay? Now, clearly, you would agree. I'm going to use two different colors here. Here's my red. There it is. Okay. You would agree that when I start, this purple color will be the undissociated acid. And this red color will be the base, the acetate anion. And you would agree that when I start, very little of the acetic acid is dissociated. But once I add an equivalent amount of base, right, then I'm going to have converted all of the acid into its conjugate base. And so if I draw a line that represents this, this is what I get. Conversely, you would agree that at the beginning, right, at the very beginning, I have almost no acetate anion because acetic acid we've gone through. It's a terrible acid. It's a really weak acid. Okay? And at some point here, I'm going to have, once I add enough base, a complete equivalent to all the acid, I've basically consumed all the acid, and now everything I have left must be the acetate anion. And so, if I do this correctly, I have a nice curve that looks like that. And I'd like you to notice, obviously, as you can guess, that these lines should cross. I should have the equal amount right here at half of an equivalent.